we're going to look at the properties of polynomial functions. So they've given us some information about a function we're going to deal with, and we're going to piece it together. We're going to try to build the equation of this function, figure out any unknown variables, and then we're going to rewrite it after. So they give us the roots. The root of the function, or the roots of the function, are -3, -4, -3, and 2. The root is quadratic, and at -3, the root is quadratic at -4 and cubic at -3. So those are important. I'm going to talk about what those are. Has a y-intercept of -172.8, and we got to find the factored and standard form of this polynomial. So what we want to do here, very first thing, is we want to start in factored form because they've given us the roots. And it's also really hard to just build any function at all straight into standard form. It's usually easier to start with a factored, or sometimes they call it like a vertex form. So a factored form of a polynomial is going to look something like this. F at x is equal to a value times x minus r s t down to whatever the last one is. So there's an r, there's an s, and then whatever your final one is. So you can keep building these. There could be so many roots to it, okay? This is kind of the quadratic one expanded. So what we're going to do is we have 3 roots here. So ours is actually, we're going to say x minus, we'll just call it t. So because we have 3 roots, we're going to have 3 sets of factored forms. Okay, so 1, 2, 3 brackets because there's 3 roots here. But they've also told us that it is quadratic at -4 and cubic at -3. In other words, what that means is one of the brackets, the one that is quadratic with the root of -4, is going to be to the power of 2. And the one that is cubic is going to be to the power of 3. So this is going to be a highly or pretty large polynomial here. Okay, and I think I'm going to scrap the standard form because that's going to take really, really long now that I looked at how large this is going to be, but we'll talk about it at the end. Okay, so in order to fill in this information, we still don't know what our a is, so we'll keep that at a. We plug in our value, so x minus, and we can call whatever we want our r value. So I can say that -4 is. So when I plug it in, it's actually subtract -4, which essentially is going to create a positive in there. The other thing we have to be aware of is because we said it's quadratic at -4, that this bracket is now going to be squared. Okay. The next one, we'll say that's the -3. So we're going to subtract, again, -3. So again, it's going to look like this positive. And we have to be aware that at -3 we said it was cubic, so it's going to have a power of 3. And finally, the last one, x minus the value of +2, so you would just write 2 in. And this one's technically to the power of 1. I could have said it's linear there, and what that means is it's kind of crossing it in a straight line. So let's talk about what each of these are. Let's simplify them and then talk about what each of these are. So f at x is equal to a x plus 4 to the power of 2, x plus 3 to the power of 3, and x minus 2 to the power of 1. These powers essentially tell us what's kind of happening at those x-intercepts. So let's just do like a rough grid here, and I'm going to spread it out because -4 and -3 are pretty close together. But at -4, -3, and the value of 2, okay? At -4, we're at the power of 2, so I'm going to write it like this. That's how they usually write it in computer language. And what that means is it's doing some type of quadratic move. Okay, so it's either coming down and just touching it, so it's like tangent at that point, or it could be coming up and just touching it. We haven't decided what quadrants this start and finish in yet, okay? But it's making that. So in other words, like think of it like almost the vertex of a quadratic is touching that x-intercept. A cubic one, if you're familiar with cubic functions, is they tend to do, in racing, it's called like a chicane. It would come down, go over, and back across. So it kind of looks like that. But right at that spot, that was poorly done. So it's making this type of gesture at that point. Okay, and it might be really, really minuscule. Assuming we've drawn this quadratic right, it means it comes down and crosses funny at like that, and then keeps coming down again. Okay, and then finally, because this is the power of 1, it's got a linear relationship at 2. In other words, it's just kind of like a straight line. It's coming through that root. So those powers tell us what's happening. That one's power of 3, and this one's power of 1. What happens at each of those roots. So it really helps us draw what our function's general idea is going to be. Okay. The other thing we need to find out is what our a value is, and that can really help us graph what we're going to do. So because they've given us a y-intercept, that's an entire coordinate, an x and a y value. So if the y-intercept we said was at -172.8, so it obviously goes very, very far down there. That means we have a coordinate of 0, the x value, and the y value is negative 172.8. So we're going to use that to build the rest of this factored form.
Yeah.
Okay? So f at x is equal to, a is still unknown. And I'm going to get rid of f at x. F at x is now our y value. Okay? So we replace f at x. Actually, I'll just highlight what we're going to replace first. X plus 4 squared, x plus 3 cubed, and x minus 2. And our x values are all going to be replaced with 0, which makes things pretty simple to work with. So we have negative 172.8 is equal to a. And then we have 0 plus 4 squared, 0 plus 3 squared, and 0 minus 2 to the power of 1. We can simplify our brackets, and the whole goal here is just, it's simple algebra. We need to isolate for this a value. Okay? So on the left side, we still have 172.8 is equal to a. This becomes 4 squared, which is 16. 3 cubed, okay, which would be 27. And negative 2 to the power of 1, which is negative 2. So all of these are going to equate to a value. Let's see if we can get something here. 16 times 27 times 2, and we know it's going to be a negative value, is 864. Okay, so we have 172.8 is equal to, I'm going to write it like a coefficient in front of 864 times a. So think of it like it's a coefficient. To isolate a, we just have to bring over this 864 and divide by it. And again, sorry, that was a negative 864. So we're going to have to divide by negative 864. So our a value in this factor form is going to be 1. They're both negative, so it's going to be a positive value. Yeah, so I'm just going to write them in as positive. 172.8 divided by 864. 0.2. So if you have a calculator that does fractions and stuff, I'm going to write it as a fraction. 0.2 is 1 over 5 as a fraction. But it doesn't matter if you write it this way or you write it as a decimal. What we do need to do is finally write out the rest of the equation. So f at x is equal to, our a value is now 1/5, x plus 4 squared, x plus 3 cubed, and x minus 2 to the power of 1. And that's our factored form of the equation. We've now written in factored form. We might want to know what the power of this polynomial is going to be. Okay, we know it's positive. So what is the power of this polynomial? Well, this is 2, this is 3, and this is 1. You can essentially just add up the values on the outsides of the brackets. Okay, so you got 2, 3, 4, 5, 6. So we know this is going to be some polynomial. X is equal to, we know the a value is 1 over 5. And x to the power of 6, and then there's the rest of the function, whatever it is in standard form. Because it's to the power of 6 and it's positive, we can get some more information about what it's going to look like. It's going to be very similar to a quartic or a quadratic, where it's going to start in our quadrant 2 and then eventually end up in our quadrant 1. Okay. So it goes from 2 to 1 because the a value is positive and it is an even has an even power, okay? And there's a couple turns in and out. We know that the y-intercept's really, really low. So we could have given it a general sketch. I'm not going to put it in standard form. In order to do that, you need to FOIL these. So you're going to have a ton of brackets, which is a lot of work there, and then eventually distribute to 1/5. We could do it, but it's just really tedious stuff. As long as you know how to use expanded form, you can kind of go from here. Let's do a general sketch, and then I'll show you what the actual function looks like on a graphing calculator. So we said that our x-intercepts were at -4, -3. Ours is a little exaggerated here, okay? And 2. It's not quite the scale, but it's a general sketch. We said it starts in quadrant 2, so it's coming down to quadrant 2, like we said before, because it's to the power of 2 at that point. It does some kind of quadratic, so it comes back up, which means it must come back down because eventually it has another root at -3. And it's known in racing as like a chicane. And then it crosses, and we know it ends heading in a positive direction in quadrant 1, so it must cross this x-intercept and carry on this way forever. The y value, or sorry, the y-intercept is at 0 and -172.8. 72.8. Not quite to scale, but that's essentially the general idea of what this function's doing. And here we have the function. So you can see that it does make a turn right there. It has a local maximum value there. And it's much more exaggerated than what we had drawn. There's our y-intercept, and there's our absolute minimum value for our function. Okay.